Hey then, I guess I'll take it away. Hi everybody. I'm Dr. Yvette Cendes, KB3HTS, and I just started at the University of Oregon in September as an assistant professor in the Department of Physics, but I'm a radio astronomer with a long history in ham radio and now doing DX at much greater distances. This is one of the telescopes I use here. This is the Very Large Array in New Mexico. So what I'm going to do here is I'm going to kind of talk about my journey in radio combined with some fun astronomy science that I've done along the way, some various examples and things like that. I don't know the exact timing of this. Due to the nature of the size of people, maybe we could do questions at the end as my initial thing instead of people maybe butting in. But I might pause for questions on the way. Yeah, I'm gonna get going here. Very quickly, what I do specifically within radio astronomy, what we're gonna build toward is called transient radio astronomy. So most things in our universe don't really change on human timescales, like your galaxy is always gonna look like a galaxy for your entire lifetime. But every once in a while, we have some things that change rapidly over human timescales. So if a star explodes or a black hole shreds a star, other giant space explosions primarily are what cause what we call these transient signals, and that's what I'm going to focus on in my talk today. But before I even was thinking about that, to begin, my ham radio origin story. I first got my tech license at age 16 when I was assigned KB3HTS. I grew up in Pittsburgh, Pennsylvania, for those who were wondering where in Threeland. Basically because I saw the movie Contact and read the book, and I just wanted to be Ellie Arroway when I grew up, full disclosure. Yeah, this is two pictures from me in undergrad. I was very involved in my college radio station, which was W8EDU, which is at Case Western Reserve University in Cleveland, Ohio, and is still a pretty active club today. It's a fantastic station because they basically built a blockhouse on the top of an 8-story engineering building and put two 50-foot antennas on top. So you could basically talk to anybody anywhere from that station. It was a pretty fantastic setup. We do a lot of contesting, we do things like that. I mainly have always enjoyed phone. I never really got into CW or anything like that. But as a quick nerd brag moment, that station, I mean, granted, was also good. We had very good supportive alumni as well. But I did once single-handedly set the record for November sweepstakes at a university station in the Great Lakes region. So that was like a pretty crazy weekend of just contacting everyone for those who have done sweepstakes. So I feel like I had my, contesting street cred when I was in undergrad. Unfortunately, I haven't really managed to do much since then because, it's tough when you have such a nice station. It's a very different story. Another one that's kind of funny is I'll say I was the nerdiest cover girl ever. So this is actually a picture. Some of you guys probably have this at your house. This is the third edition of the ham radio license manual. And you see me. If you have the manual, the person you're looking for is in this corner. So this was me while I was contesting. Somebody snapped a picture and I did a quick peace symbol because I was just trying to get them to stop bothering me. And I ended up on the cover of the tech manual for the third edition. So that was pretty fun. That was probably about 10 years ago. But anyway, yeah, I was doing a lot of ham radio. I was doing a physics degree at the time at Case, and I did a master's degree as well in physics. Probably the coolest nerd moment, though, in my career as an astronomer as well. My first real radio astronomy experience happened then, which was doing a research experience for undergraduates, or REU, which is a fancy summer internship basically at the SETI Institute, which is down in California, working with Jill Tarter, who's here on the left. Some years after my internship, we met up again for cocktails, and we took this picture then. Jill Tarter, for those of you who aren't familiar, is actually the inspiration for Ellie Arroway in the movie Contact. I got to work for her for a summer, and I always say that she was the most intelligently intimidating person I've ever met. But I don't really mean that in a bad way. I just mean that she was a, amazing person who's on a very different wavelength from all the rest of us type thing. Very dedicated to finding signals from outer space, basically. What we were using at the time was this telescope on the right, which I actually include here because it's also the closest radio telescope to us here at the University of Oregon. This is the Allen Telescope Array. It's right next to Mount Lassen, so it's about a 5.5-hour drive. So this is Mount Lassen here. And here is part of the Allen Telescope Array. So if you're ever down there in the summer, they do actually do tours of it. So just putting that out there for anybody who's interested. Anyway, so, I know we have a lot of people who vary in levels of radio experience here. I'm not as sure how much on the science side or the astronomy side you guys have, so I'm just going to go through a bit of background. Why do we care about radio astronomy? And what do I mean when I specifically talk about it? So the first thing we have to think about is that the Earth's atmosphere blocks some wavelengths. So, we have our atmosphere. We really like it because it keeps us alive. It also blocks various bits of the spectrum. So here, for example, visible light, if you look up at the night sky, you'll see some twinkling of the stars, and that's because it's not perfectly transparent at our optical eye wavelengths. You'll see a little bit of twinkling. That's basically because the atmosphere is interacting with the starlight as it reaches us. If you go further to higher wavelengths, though, so gamma rays, X-rays, UV are actually completely blocked by the upper atmosphere. Thankfully for us, we don't really want to be bathed in gamma radiation and X-rays and things like that. A lot of infrared as well. That's why you actually have to launch the James Webb Space Telescope and send it off into space, is because you can't look at those wavelengths from Earth. However, you get down to these lower wavelengths and something very cool happens. Radio waves are basically completely transparent if you're at a certain range. The gigahertz range is primarily where the science is happening that I'm going to talk about today. As many ham radio operators know, as you go to the longer wavelength stuff, those wavelengths become blocked again. As we know, if you have a solar flare and you have the ionospheric skip effect, long wavelength here basically means down at those lowest frequencies. So what I'm talking about here, it's closer to 80 meters and above, I guess is the ham radio speak for the wavelengths I'm talking about in this thing. But anyway, so as we all know, radio is very cool because we can do all these things from the ground that we can't necessarily do from other wavelengths. And what we end up seeing, though, is also very exciting. So, you have your optical eye. If you look up and it was a very dark sky sight, then this is what you'd see. You'd see a lot of stars, you'd see galaxies, the Milky Way, maybe a comet, things like that. And if you have radio eyes, though, now I'm going to show you guys what the sky would look like. So if you looked up with radio eyes at the sky looks incredibly different. What we see here instead of all these little dots, for the most part, if you're looking here, these are pretty much all not stars. What these are actually, they're supermassive black holes called active galactic nuclei, which are feeding on dust and gas, these supermassive black holes in galaxies millions and millions of light years away from us, feeding on that gas, and then there's radio emission that we can see from there. You're also going to see these complicated structures. You're going to see these weird whirls and loops. These are supernova remnants in our own galaxies for the most part. So, thousands or hundreds or thousands of light years away from us, but relatively astronomically nearby. And you can see emission from those still in radio. So different physical processes give off different types of emission. As you can see, if you want to study things like black holes, radio is actually a really, really good place to do it. So moving on, I'm going to talk about how radio astronomy works. So I have this picture here because, as I said, I wanted to be Ellie Arroway when I grew up, and I kind of got to do that in some senses. Anyway, but I do need to tell you guys a bit about how radio astronomy works. So first of all, this picture is taken at the Very Large Array, the VLA in New Mexico, and I use telescopes like the VLA to look for this radio transient emission that I'm going to talk about in this talk. The first thing to mention is we don't actually listen to the signals. These signals are too faint and you'd only hear static if you tried. So this is actually not true in this image. For those of you who've seen the movie Contact, I have this picture because this is the famous scene where Ellie Arroway is listening and she hears the alien signal. But as you notice, this is actually not even plugged into anything. So, never overdo anything for a nice picture. The fun thing I should mention also about this picture is it's actually on the National Radio Astronomy Observatory website as to explain how we don't listen to radio signals. So that's kind of a funny thing to me. Anyway, the final thing to mention that is not true in this image is I actually don't visit these telescopes to observe. These days, like anything, it's done fully remotely. We have observations we will propose for these observations 6 months a year. Actually, anybody in the world can apply for time on the Very Large Array, for example. You just have to make a very good scientific case on why you need that time. But I should mention, even high school students have gotten time on the VLA. Ham radio operators definitely have also gotten time for various projects, or, you're usually working with another astronomer who knows the technical side better and things like that. Once you get this time, though, you put your observations online. An observer there will take the data, and then you'll download it once it's complete. So, I mean, that's obviously less romantic than basically going on the equivalent of a D expedition to get your faraway radio data. But it is a lot more convenient that my students can set these up. And then once it's taken, we can download the data here in Eugene and process all the data here ourselves. So anyway, I'm just going to check, make sure if there's any very important technical questions here. Yeah, okay. We're good. I'm going to keep going then. So to continue on, this is just kind of a quick background of what I studied undergrad, a master's degree. But then I decided to do something different. So my physics background, well, undergrad master's is actually in cosmic ray physics. So something a little bit different. But I always, as you can tell, wanted to be a radio astronomer. So this is something I decided to pursue actually in a very different way, which was I went to the Netherlands and did my PhD in astronomy while I was living there. I lived there for 5 years. And I lived in Amsterdam for 5 years, which is the picture on the top. And then I ended up living on the bottom in Toronto. And my degree is from Leiden University in the Netherlands. So this is kind of like a side note to any students who are listening, who are thinking about graduate school, things like that. I actually had a bit of trouble in my PhD. And what I'm saying about this is I was hired to work on an instrument in the Netherlands that never really worked. It was called LOFAR. It was low frequencies, so kind of like 140-ish megahertz for range. It never really worked because it turns out the sensitivity of that instrument just never got to where it was supposed to be. More importantly, though, the advisor I started out with, in hindsight, never really took me seriously as a scientist. And, hindsight is 2020. The point is, like, I started in Amsterdam. I ended up having to switch advisors, and that's why I was in Toronto for a while, and then I was in Leiden with, another university I ended up transferring to get this PhD. So this is just kind of like telling grad students, be mindful when you start out, ask questions about the supervision that you're going to have. Be aware it doesn't always work out. But I will say, I think at the end of the day, it was worth the struggle of finding the right person to do science with, things like that. I finally got my PhD. It was May 2020, so I got to do a virtual defense. So here's the picture of my virtual defense. Anyway, so that's like kind of a very brief, on the academic side of things, story about my PhD. The thing I will say, the Netherlands, I actually did love living there. It was a pretty fun place. I met my husband there, so, best souvenir ever. And my fun ham radio thing is I also actually got to do moon bounce in the Netherlands. So I thought I would pause for a minute to mention this. So the Netherlands has had a very long tradition of doing radio astronomy because it's a very flat and cloudy country, somewhat similar to Oregon in some ways. And as you saw, radio waves do not care about clouds. They come straight through. So on the left here, this is actually, it's called the Dwingelo Radio Observatory. So this is a 25-meter dish that in 1956 was actually the biggest in the world for like 1 year or less than a year, the biggest radio telescope in the world. And it's now actually completely used by amateur ham radio operators. There's a club. I have to look up the call sign exactly, but I mean, it's pretty easy to find them. And they do a lot of cool things. Like it's the only time I ever actually heard a radio signal was at Dwingelo. I actually heard a pulsar. I was like, okay, that's pretty cool. This picture on the left here is the sun. They use the sun. The telescope was pointed directly at the sun because the sun is the brightest thing in the sky most times. And it's a very great calibrator for your telescope. And on the right here, this was me doing moon bounce when I was there, which is, Dwingelo, you pointed at the moon, you bounce the signal off. So it was pretty cool, to talk to somebody in Poland, which is about 500 miles away from you, plus, 500,000 miles for the distance. And the thing that was very weird about it is, you do have the lag of your signal of a couple seconds bouncing to the moon and then bouncing back when you talk to someone there. So just for this audience, I thought I would mention this story because that was a pretty cool experience. But anyway, I'm going to tell you guys a bit about my research astronomy, though, like what I ended up doing in my thesis once I found the good advisor and all these things, which was radio observations of supernovae. So supernova is what happens when a supermassive star reaches the end of its life and dies in a fiery explosion. So to begin, here we are again with our optical image. This is if you were to look out in the night sky right now. Here are stars. And we have some familiar stars for those of you guys who know astronomy. You might find a few familiar ones here. So here we have Orion's belt. A lot of people, that's one of the few things they can find in the sky. It makes up part of the constellation of Orion. Orion is a fun constellation because it actually kind of looks like what we're talking about here. So this is, he's a hunter. He has a belt. He has a shoulder star up here called Betelgeuse. Rigel is one of the foot stars. He has some head stars. He even has a sword. And if you follow, this is a fun fact, if you follow Orion's belt all the way down here, you will see a bright star called Sirius, and that's actually the brightest star in our sky. So as I said, Orion's a good constellation to know, very prominent in the winter sky. It's also a very cool constellation because it has a lot of different kinds of stars in it. And Betelgeuse, you might have heard, is a star that is going to explode astronomically soon. I will explain in a second what exactly I mean by that. So all stars are actually different sizes in the sky, different brightnesses, things like that. And so when I mean a supermassive star, as I said, the supermassive stars are different. So our sun here is up in the upper left here, if you can see my mouse, is a very small star compared to, say, Sirius. Sirius is the brightest star in the sky. It's about 4 times the mass of the sun. It's the brightest because it's about 8 light years away from us. So it's basically very bright because it's a bigger star and also very, very close to us. Rigel, that foot star that I pointed out earlier, though, is a significantly bigger star. It's about 600 light years away from us. So as you can tell, we're getting to greater distances, much bigger stars, though, much brighter. And Betelgeuse is just, absolutely so big. It doesn't even fit onto this entire thing. It's, I'm trying to remember. I think it's roughly about 8 times the mass of the sun, something like that. Toward the end of their lives, however, stars will swell up into very, very big sizes, and they will eventually go supernova. I don't have enough time to go through all the stellar physics of how this happens. All I will say, though, is when people tell you Betelgeuse is going to explode soon, they don't mean like tomorrow, most likely. They mean more like tens of thousands of years, because if stars live, millions of years, that's like pretty close to the end of their lives. Like, could always happen, but we're fairly confident we'd understand stellar evolution. Betelgeuse is probably not the most likely star to explode in our sky. Sorry about that. Anyway, though, so we're talking about a stellar explosion. And what I said earlier is that supermassive stars are the ones that explode. That's about 1% of all stars, or less than 1% of all stars count as supermassive. That means about 8 times the mass of our sun. And yeah, supermassive stars really are the rock stars of our universe. So they shine very bright, they burn very fast, and they die young. And when they die in fiery explosions. So this is a supernova explosion, or artist's conception of one. As you can see, you have a shock wave that will go out. The star will be completely torn apart. And suddenly you have a very complex environment from the shock wave that's gone out. You have the formation of what's called a supernova remnant that begins around this star. And the amazing thing, side note, about supernova, and the reason we know a lot about them is we've actually seen them throughout recorded history, like our ancestors have seen them. So this is actually supernova AD 1954. There was a guest star that was seen in the sky in the summertime that year, and it was visible for 2 years to the naked eye. The Chinese, who are very good astronomers, saw it. Japanese, Arabian astronomers saw it. There's also possible reports of it in Europe and in Chaco Canyon in Arizona. Yes, New Mexico. There's actually, they think the supernova in the sky in relation to where the moon would have been a pictogram. You can actually go hike there and see it. So supernovae are a thing that we've seen a lot of times over history, these guest stars. And the thing that's really cool is the Chinese in particular are very good astronomers, and they would record, the equivalent of coordinates for where these things were in the sky. And today we can actually go point our telescopes at these coordinates, and this is what we see for the AD 1054 explosion. I don't know about you, to me this looks like there's a giant explosion that happened here. This is a Hubble telescope image. And the amazing thing is that it's actually 10 light years across. So it takes light 10 years to go from one end to the other of this giant explosion. And this is, by the way, it's about 6,500 light years away from us. So this light took 6,500 years to reach us, which is kind of also a very cool thing, and then I guess it was plus 1,000 years at this point. So anyway, we've seen supernova. Well, the thing about the universe, though, if you look out in optical eyes, they have another thing that's a little bit of a problem. If you're looking at this optical image of the Milky Way, you'll notice these dark patches here, and that's basically the problem is there's a lot of dust in the Milky Way, which invisible light will affect us. You won't be able to see through that. So the last supernova we have seen and recorded in our own galaxy was circa 1604. It's called Kepler's supernova. Galileo saw it, but he didn't have his telescope yet to kind of give you a perspective of where we were. And we have actually found in radio wavelengths supernova remnants that we know are younger because you can measure the expansion and kind of calculate backwards to when it would have started expanding. But they're behind dust. So basically, we never saw them. So this is actually a bit of a problem. And to give you an idea, the amount of dust we have, or the amount we can see with our optical eyes in our Milky Way galaxy in optical light, if the Milky Way was the size of the United States, you can't see further than the equivalent of the state of Virginia. Like, we're really constrained in our own galaxy to finding supernova in many ways. However, we have other ways we can look out that are not constrained in our own Milky Way. And down here, or to the right of this image, there's actually two blobs called the Large Magellanic Cloud and the Small Magellanic Cloud. And these are actually satellite galaxies to our own Milky Way. The LMC is about 170,000 light years distant. So, that's not as close as stuff in our galaxy, but compared to the Andromeda Galaxy, which is about 1 million light years away from us, the closest major galaxy to Earth, this is astronomically next door. The other nice thing is, as you can see, we have a straight shot. Well, if you're in the southern hemisphere, you have a straight shot to looking up at the Magellanic Clouds. So astronomers do that quite a bit. And because if you do that, you see this. This is a giant complex structure called the Tarantula Nebula. A nebula is gas where stars are being formed. Some of the biggest stars that we actually know of in our own local universe, or actually know anywhere in our universe, are in the Tarantula Nebula area in the Large Magellanic Cloud. It's not that we don't think there's other stars that are equivalently large in our Milky Way, it's just we can't see them, and you have a straight shot to look up and see this Tarantula Nebula. And so you heard me say earlier, the biggest stars are the ones that go supernova. So, it's a pretty interesting place to keep an eye out. And something very exciting happened actually in 1987 in this area of the sky, which is called Supernova 1987A. So Supernova 1987A is a fun story. It was discovered in February 24, 1987. It was the first supernova of the year. That's why it's Supernova 1987A. Happened in the Large Magellanic Cloud. It's the closest supernova that we've been able to observe since the invention of the telescope. So it's very, very important in astronomy. Side note, it has a lot of firsts associated with it. One of the first is it's the first time we actually had a star that we saw and then it exploded. So we know the progenitor is what you call that in astronomy. So that's a pretty important thing for us. The story of how it was actually discovered is also pretty fun. So it was a University of Toronto astronomer named Ian Shelton, who I met when I was studying in Toronto for a couple of years. And Ian Shelton was working in Las Campañas Observatory in Chile. He was doing some tests on a University of Toronto telescope. In the 1980s, they would do exposures not digitally, but on these giant glass plates. You would basically put photo emulsion on the plate and expose it to the sky at the telescope. And that's how we would take data. And he was doing some sort of test, wasn't really working. So he called it a night kind of early. The conditions weren't great, blah, blah, blah. But he did something very smart, which was he took a look at his data before he went to bed. And when he did that, and when he developed the plates and looked at them, he's like, there's a really bright star there. That star is so bright that if I go out, I should be able to see it with my naked eye. So he stepped outside, looked up, and realized that he saw a supernova. So he's the first person to realize, he's seeing a supernova in hundreds and hundreds of years. Nobody had really done that before. There was another collaborator working there at that night. So he's like, hey, do you see this? That guy said yes. This is also the 1980s. So the long distance telephone lines were down. They ended up having to drive several hours to the closest village where there's a telegraph that they could send in to get credit for the discovery. But it's lucky that they did because they weren't the only people who ended up reporting the discovery that night. It was just that they were first. So, if you want eternal fame and fortune, I tell my students, you should always take a look at your data before you go to bed. Anyway, so supernova 1987A is a pretty cool object. This is what you see though, if you were to look today, the supernova is of course since faded. This is a Hubble telescope image of the supernova. Now it's a complex environment, so I'm going to show you guys really quickly what it looks like if we were to look sideways at it. So what you see here is the innermost bit here is a supernova remnant. It has a weird angle to us, so this is just if you had the artist's conception of not looking at the specific geometry that we have looking toward it. You have an inner ring of dust and gas, and you have further out hourglass rings. These are all basically mass loss that the star had before it died, in the tens of thousands of years before it died. Okay, so I've now told you guys a whole bunch about supernova. What does this have to do with what I do? So since supernova 1987A happened, basically the first couple days there was some radio emission detected from this source. It was from a radio telescope in Australia. They think that has to do with the supernova explosion itself, but they redetected emission in 1990, and that emission is basically, I showed you that video earlier of a shock wave going out from the supernova. I showed you guys how there's these rings of complex structure around it. As the shockwave basically goes out, it's obliterating those rings, and that gives off a burst of radio emission, and that's what we can study. So you can't study it with the VLA because that's a Northern Hemisphere telescope. You can study it, however, in the Southern Hemisphere. This is the Australia Telescope Compact Array, or ATCA. ATCA is this is basically a huge telescope. This is actually a railroad track. These telescopes are the size of buildings, and you can move the antennas back and forth depending on the type of science you want to do. So that's pretty cool. And basically since ATCA came online in the early 1990s, we've been taking 9 gigahertz ATCA observations roughly every 6 to 12 months to see what's going on with this supernova. And, if you have images that last for decades, what should you do? You should, of course, make a cool movie. And so this is basically what radio data looks like. We're basically making pictures from our radio information. And I'm going to let this loop for a couple times, don't worry. But you can see that there's a lot of interesting things going on. Well, okay, I think it's interesting. Anyway, so what we're seeing here is, I'm going to let it start again. You have this ring, as I said, it's that shockwave going through, interacting with the emission. You start seeing, it gets brighter, roughly on one side, roughly around 2003, it starts getting brighter faster. So this is the sort of things that we're interested in as astronomers. It looks like this explosion was asymmetric, for example. One side lit up faster than the other side. That tells you a lot about how the supernova explosion happened. It starts lighting up around 2003 because it turns out, if you look at the Hubble data, corresponds with when that shock wave went into that innermost ring around supernova 1987A. And that's basically, why it lights up. You have more dust, more radio emission comes from that. I'm actually going to show you guys another version of this. So I also cross-stitch as one of my hobbies. So this is actually cross-stitch supernova 1987A in radio, and this is actually the first figure from the paper I did with my advisor in Toronto. And I cross-stitched this for him as a gift when I finished my PhD because it was such a big thing, but for his assistants to help me finish. But so, yeah, this is radio data. It's purely pixels, like exactly the same as the radio data would be. The coordinates are accurate. This is the beam size is what it's called. So that's the resolution your radio telescope has on the sky. And what you can see is, as I said, you can see it lights up. You can see over time, it does remain asymmetric. This last observation was from 2017, so toward the end of my PhD thesis project on this object. And what we did find, my discovery, or my whatever you want to call it, at the time for supernova 1987A, was that the shockwave had actually left that innermost ring. It had completely destroyed it. It's going outward. We need another student to go look at it because people are like, what has it been doing since? And it's like, well, actually, we don't know. We're a little manpower limited. So that's an example of what we do in radio astronomy. And also I'd point out, this is the best you're going to see for a radio image of a supernova explosion until we find the supernova in our own galaxy. So, feast your eyes on my ultimate DX project here. So moving on, my career as a radio astronomer. After I finally finished my PhD, I then did a postdoc at the Harvard Smithsonian Center for Astrophysics, which I'm standing in front of the building here. It's in Cambridge, Massachusetts. And I was working on all sorts of radio transients. So natural exoplanet emission. So if you had a magnetic field from an exoplanet, you could get bursty emission. We were looking for that. I still co-advise a student, in fact, looking for that. Gamma ray bursts, so stars that die and have extra fiery explosions, and tidal disruption events, or TDEs, which is going to be the rest of my talk because I only have so much more time here. So a TDE, or tidal disruption event, is what happens when you have a supermassive black hole and it's torn apart by tidal forces. So I have a pretty cool artist conception video of what this is like. So this is a supermassive black hole in a galaxy millions and millions of light years away from us. And somewhere over here, yeah, so we have the supermassive black hole. Yeah, here we have a star, and this star is about to have a very bad day. So for whatever reason, this star has been sent in on a gravitational trajectory that it's going to send it too close to the supermassive black hole. And so, the star is going in. It's starting to stretch. You see in the video, this is actually called spaghettification is the technical term. And then, yeah, so the star gets disrupted in a very quick period of time, like a few hours, which in astronomy is like nothing. About half the star gets flung outward. Half the star goes into this accretion disk that you can see swirling around. And you suddenly have this very chaotic system around this supermassive black hole that you did not have before the before the TDE happened. You can have jets even launching. You saw in that video in about 1% of all cases. We think we have these relativistic jets. I'll talk about those a little bit more in the future. And yeah, so suddenly a very complicated environment. There's a lot of physics we can study in this environment that we can't study otherwise. To date, there's been about 100 TDEs that have been reported. Most have been discovered in optical wavelengths by these giant supernova surveys, and then we'll follow up in radio observations. And the reason we're interested in doing that is because we want to trace the outflow of material post-disruption. So this is a slightly technical slide for the science, but I'm just showing it very quickly for those who are maybe interested in the more technical details. What are we actually doing in radio? So what I do as a radio astronomer is, I have my frequency spectrum here. I'm taking a bunch of observations, let's say from 1 gigahertz to 20 gigahertz. I basically take these radio observations, I make a radio image from those observations, and I'm basically then measuring the flux or brightness at each of those frequencies, and then I get a light curve, so the flux density here. The light curve is going to have these different breaks in it in the spectrum, so I am interested in things like what is the frequency where it's the brightest, but then I'm interested in these other things, the other breaks that I see, and then there's a lot of complicated physics that happens that I'm not going to get into for this talk, but I can extract a ton of physical parameters from this radio information. What I mean by physical parameters are things like the radius of the outflow, its energy, the density of material it's plowing into, the magnetic fields, all sorts of things that tell us about this environment that we wouldn't otherwise know. So radio is very, very powerful for studying TDEs. I said I would talk about jets in radio, so I'm just going to spend a moment explaining what exactly this means because it's actually a very big part of radio astronomy in general. So radio jets are basically jets of material, as the name says. It's basically just gas that is shooting out from the environment around the supermassive black hole. I should emphasize it's not coming from within the black hole. Nothing can escape a black hole once you pass the event horizon. This is material that comes inward, spirals around the black hole, gets launched out at basically close to the speed of light. We say relativistic because you have to take into account Einstein's relativity to explain it. These jets can be absolutely ginormous, so like 100,000 light years across, so the size of our galaxy in this beam of radio emission. And then we will see these in radio because as these electrons are spiraling in magnetic fields, it's called synchrotron emission. That's what we're studying. So this image here on the right is actually from the Meerkat telescope in South Africa, which is a radio telescope, which is also in gigahertz. Meerkat, though, is a very unique telescope because it has a very large field of view, up to a square degree of sky. For reference, the moon is about half a square degree of sky, like when you're looking at the moon. So it's a pretty big wide field. I'm interested in, one of these little dots. It's here. It's actually one of the little dots over here. Of course, I cut it off here in this image. But what you see here, I love this. This is as pretty as radio data gets. You have these complicated jets here. So these are two examples of jets. So this is the black hole lives here. You see these lobes going outwards in both directions. This is about, I believe it was 40 kiloparsecs. So this is about 200 million light years away from us, this galaxy. This one is completely coincidentally, it's like 100 million light years further away, but it just happens to be in the same line of sight. And you see it as a complicated swirl as it goes outward. This material basically becomes a giant fluid dynamics problem as this material goes outward. It should be emphasized, like this jet, it does have a counterjet, we believe, but it's called Doppler boosting. It's basically going the equivalent of faster than the speed of light in our reference frame. So we will never be able to observe that counterjet. And physics is very cool. The final thing to mention, because this is a radio crowd, all these lines here, this is just calibration artifacts that you have because you have a bright radio source. So you're always going to have some slight calibration stuff, of course, in radio astronomy. So, yes.
Can I heat the fire, Tom?
Just touch it off with this torch.
It's what?
I'm going to bed in an hour.
Anyway, somebody should mute.
It's 76.
Anyway, I'm going to keep going on here. Yeah, so as I said, I use telescopes like the Very Large Array here in New Mexico to do all this type of stuff with these TDEs. And I'm going to, just very, very briefly with the time we have left, go through, there's two major categories of TDE out there. So 99% of all tidal disruption events that we see out in the universe are what we call non-relativistic. So you have an outflow that will happen when this TDE occurs, and it's about 10% the speed of light. So that sounds like a lot, but that's actually pretty similar to what we see in, say, supernova 1987A in terms of the velocities that we're measuring as that shockwave goes outward. You don't have to take relativity into account when you do your physics calculation. 1% of all cases, though, are different. You have as one of these relativistic jets that launches. So that's pretty interesting and unusual because there's a lot we don't understand about these jets. So if you can see one of them growing and starting, then hey, that's a pretty cool thing to study. So I'm going to wrap up with kind of my biggest scientific claim to fame recently, and probably why I got hired by the University of Oregon, which is called late time emission. So as I said, doing all these radio observations, most radio TD observations traditionally occurred within 1 to 2 months of the optical detection of the TDE. And then about 20% of TDEs would be detected in the radio during this time. There's various reasons for that. You could imagine if you have an explosion, then usually if you're most likely to see something in the first couple months. And also radio telescope time is a very precious resource. The VLA, for example, has about four times more hours applied than their literal hours that they could allocate. So it's very competitive, and you're going to do other things usually with your precious radio time if you're not seeing anything at earlier times. But then recently, there were two cases of TDEs, Assassin 15OI and IPTF 16FNL, that became radio bright over 100 days after the initial TDE happened. So then you could ask yourself, is this common? Are we overlooking something in the TDE population that we weren't seeing before? So to figure this out, we did a campaign. We looked within the Very Large Array Sky Survey. The VLA does a sky survey roughly every 18 months. They look at the sky to see what's going on. And then we also did dedicated observations that gives you a more detailed look at what's going on in a certain patch of sky. And it was about 25 older TDEs. Older here means 2 to 3 years old. And these were all TDEs that had no prior radio emission detected. So I'm going to show a plot. Please forgive me for doing so, but I'm going to talk you through it. Just so you can kind of get why one of these discoveries is pretty interesting. So this is time since the discovery of the TDE in days. On the x-axis, the y-axis here is luminosity. So if we adjusted for brightness for distance is what luminosity means. We have various TDEs here. So up here is a jetted TDE, a very famous one called Swift J1644 plus 57. what you can see is it's much more luminous than the non-relativistic TDE here. The yellow one is called AT 2019 DSG. I'm sorry, these names are all terrible, I know, but I didn't name them. The surveys that discover them name them. And then anyway, so you have then Assassin 150I here, which is the TDE that if you have a triangle, that means you didn't detect anything. And then you have an X, that means you detected it. So, oh, looky, it's wow, suddenly very bright. Did a second bump here. That's, since been fading. And anyway, we made a very exciting discovery, and I'm going to bring that one into the mix. And this is called AT 2018 HYZ. So this was a TDE that was discovered in October 2018. It was actually an in-house TDE in Harvard. One of our PhD students at the time discovered it. So we know it very well. It's actually a very boring TDE as far as these things go, very garden variety. But then, I was basically looking at this survey data, and what I discovered is this sudden astronomical rise. So this is actually, it was detected in June 2021. And when we discovered it, it was rising as fast as T to the fifth at 5 gigahertz. So for those of you who know physics, T to the fifth is insanely hard to explain. Like acceleration is a T to the third value, for example, velocity is T squared. So something that's going as T to the fifth is a very unusual, very exciting object. The cool thing is, I suddenly had to put together a multi-wavelength campaign so we could take a look. But the nice thing there is, you get these physical parameters that I was telling you guys about earlier, the radius, for example. And then what we ended up doing is, so first of all, this is so far away, you can't see it with the VLA. It's a point source, so you have to make some assumption about the geometry. Then you can make two general things. So is this outflow going out as a sphere, for example? That would be one geometrical extreme. The other could be, if it's a jet that's about 10 degrees that was pointed directly at us, that would be the other extreme. The truth is probably somewhere in between, but if we can't see it, you have to make some sort of assumptions in physics. And anyway, what we could see is, we have time and we have radius. If you did high school physics ever in your life, you actually probably could recognize this plot, because what did we do? Time, radius, you fit the intercept, you go backwards, you see, okay, it actually started, it goes to about 750 days after the initial TDE happened. This last upper limit is our last observation where no radio emission was detected in a survey. So this is actually, I think, pretty cool because I can show this to you. And if you've done high school students can even understand this plot when I give talks to them. So that's pretty exciting. And also because we have radius and we have time information, we can go. And then this actually corresponds with up to something about half the speed of light even. So that's pretty crazy. I am going to skip these in the interest of time. But yeah, so what we ended up doing is coming out with a exciting news result. It actually, black hole burps at half the speed of light years after devouring star. Caught us completely by surprise. And, so this was actually on NPR one day, and it was the top news story on NPR. So like we beat student debt relief that day. So that was pretty exciting. And yeah, this should also be a very familiar artist illustration of a TDE from earlier. So, this is definitely work that's caught attention of people. I am very briefly, though, going to touch on, as I said, this was one object in about 24 that we looked at in this survey. So what did the rest of the survey show? So this is that plot I was showing you guys earlier. I'm just zoomed in now to the lower luminosities here, the non-relativistic TDEs. Here is the non-relativistic ones. This is AT 2018 HYZ shooting for the moon. I should mention, by the way, it is still shooting for the moon. It's still going upward at very, very high velocity, not quite as fast as it was. But now I'm going to add in the rest of the survey. And what you see is we actually have 10 new TDEs that turned on at later times, so hundreds of days after the initial TDE happened, that we did not see at those earlier times. So this is actually unexpected in TDEs. The theorists have been very confused about this entire situation and things like that, which is a really fun place to be. They do appear to be non-relativistic TDEs. If you do the same, as I said, calculation on how these things are going, there doesn't appear to be anything there. There's some various ideas on how this outflow could happen at these very late timescales, but this is kind of what you actually do as a radio astronomer. I realize this is getting a little bit maybe into the weeds, but it turns out, about 40% of TDEs and black holes after they eat a star will have radio emission in the years later timescale that don't at earlier times. So that's been pretty exciting. We're really still trying to get into the statistics of what exactly is going on, so we can start testing some theories, but it's been a pretty exciting time. And yeah, I have a bunch of students now who are excited to look at this data and help us figure out what's happening. So kind of to wrap up here, yeah, so my career as an astronomer, the most recent thing is I began in September as an assistant professor at the University of Oregon. This is also something I'm just putting out there for students who are listening to this. I'm teaching Astro 321 in spring, which is topics of astrophysics. So if you want to learn more astrophysics, you should take this class. The prereqs are Math 252, Physics 252. Shoot me an email after this talk is done if you have any questions, but I figured I should probably advertise to this crowd if we're already talking. So just to wrap up, some final thoughts. Radio astronomy is a powerful tool for understanding radio transients and provides a unique window into physics that we can't see at other frequencies. So, you know, we all know that we like radio for ham radio people, but it really is actually that cool. For TDEs, we're really just starting to learn about this population and what it's doing. For those who want to learn more about TDEs, I actually wrote an article for Astronomy magazine that came out in their December 2021 issue, which is called How Do Black Holes Swallow Stars? So if you just search How Do Black Holes Swallow Stars in Google, it pops up, it's free. I did submit something to Scientific American, but that's not going to be out till probably sometime this summer. So that'll be, you know, the next edition, because as you see, this is a pretty fast-paced field. And yeah, take Astro 321. For those who are not interested at that level, I'm also teaching next year some of the first year non-major courses like the Astronomy 100 series. So keep an eye out for those as well. So yeah, thanks very much. I'll take any questions.
I have a question about slightly early in the presentation. You said that how do shockwaves propagate in space from the supernova?
Yeah, sure. So shockwaves propagate because space is not a perfect vacuum. You know, there is still going to be one atom per square centimeter per square meter, even when you go in between the space between galaxies. So that's basically how the shockwave is propagating outward. There is interstellar material. It's just compared to Earth, it is a vacuum.
Is the speed at which it propagates much, much lower than others, for example, because of how sparse the particles are?
Yeah, so it actually, well, it depends what starts the shockwave. The shockwave is only ever slowing down if it's hitting material. So it's basically conservation of angular momentum. So when they start from a supernova or something, for a supernova, for example, it will start close to the speed of light. It slows down very quickly. So they still go at several percent the speed of light, so it doesn't slow down that fast, I guess is the answer. Yeah.
Thank you.
Mm-hmm.
So thank you so much for this presentation. We also have a couple of questions from the chat that I wanted to bring up.
Sure.
There's one from Jay that says, if the TDE happens so quickly in our time scale, how do you catch it with the radio observations?
Sure, that's a great question. So I'm basically following up on data that my collaborators have taken or that other astronomers have taken. So in optical wavelengths, when the TDE happens, you basically get, it's an incredibly luminous flare, right? You see these from very, very far away because so much matter has been unbound so quickly is what causes all that energy and light to release. And that light will last for, you know, couple weeks, couple months. What's also happens is that you have these supernova surveys that now look at the entire sky pretty much every night. So for example, in the last year, they found about 18,000 supernovae to give you a sense of scale. And then 1 in 1,000 of those roughly right now is a TDE. And then when that is identified as a TDE, you need to take the spectrum of it. Then we will follow up with our radio telescopes.
Can we ask a question? We've got a question here.
Mm-hmm.
Okay, he wants an explanation of the picture on top.
The picture on top, this one?
Yep, the picture on top of what looks
Yeah,
like a
so
star
this
getting shredded.
is a Hubble image of supernova 1987A. So this innermost bit here is the remnant itself. This here is the gas ring that's been lit up that's emitting in the radio video that I was showing. And then these further out hourglass ones are from an even earlier period of mass loss. I think the shockwave I calculated it, and it's like, you know, in my retirement, it'll probably finally get that far. So they're much further out.
We've got another question from the chat here. So a while ago, you showed a picture, and you said that there were some radio artifacts within that picture. Someone's wondering, how do you know those are radio artifacts?
Experience, I guess is the first thing. The second, I mean, you don't see waves in the sky. I mean, let me bring up the picture again. Where is it? Here. So radio astronomy, and this is getting a kind of, so the radio astronomy I've been presenting today is an interferometer, right? So you're linking together the radio telescopes as you see them. And that ends up introducing calibration effects. So we actually, you know, will look at our calibrator to begin with in the sky, and then we will look at other calibrators, things like that, whenever we do an observation to minimize these little wavy lines. And if you do a good job, then you won't see it. If you, however, have a bright source that you're not taking into account in your calibration, you do get these wavy lines around it. So yeah, hope that answers the question.
Because your wavelengths are considerably longer than light, does that reduce the degree of angular resolution that you can achieve compared to light?
That is a good question. The answer is no. We actually have better angular resolution than what we can see in light. So basically, the wavelength and the size of your mirror, it's theta over d is the wavelength over diameter. So because we see light in nanometers, and these are such big wavelengths, it's the opposite relation. It's actually the bigger radio telescopes can get better resolution because we can co-add these antennas is the other trick. We can even, it just gets really tough with the calibration, add together telescopes all around the world. So if you've ever seen like the picture of the black hole, that's actually at radio wavelengths. That was taken by co-adding signals from literally telescopes from South Pole up to Greenland or something like that. It's just, that's very hard to do.
I had a question about the T to the fifth measurement. I'm in like the first year physics sequence, so I'm, you know, still
Yeah.
learning. So yeah, I'm like, I know that there's velocity, or there's this like the position, velocity, acceleration. I'm kind of curious about I guess what T to the fifth really means.
I mean, T to the fifth means it's rising very fast.
Okay.
And presumably there's something driving that to make it so fast. That's what it tells us. That's like the context clue. It's not that there's like physically something after acceleration and that's what we're seeing. It's just the relationship we're seeing is so crazy fast.
So someone's wondering, is it possible to study transients through audio rather than pictures?
No. So basically these signals are so faint that you would not be able to hear anything even if you tried. Just listening by audio, because our ears are not as good as image or signal processors are. Also to give you an idea of like, so these are very faint signals. The equivalent of like, so if we put a cell phone on the moon, or if you're doing EME or whatever, I mean, a cell phone on the moon would be one of the brightest radio sources in the sky. So these are a factor of thousands fainter than that. So yeah, you wouldn't unfortunately hear anything.
Doug is also wondering, is there a standard format for capturing all of the radio data regardless of what's being observed?
Yeah, I guess it's called a measurement set. I mean, so the NRAO, the National Radio Astronomy Observatory, data.archive.edu, you can go and download any of these, and there's standard pipelines you can push through. They have tutorials online. So anybody in the world can go and after initial year of proprietary time, you too could download data and image it and stuff like that. It is fairly standard in that sense. Let's see. looking in the chat, somebody's asked, are any new radio telescopes being built? Yeah, so the Square Kilometer Array is kind of actually under construction now, finishing some first phase or something. So the Square Kilometer Array is going to be in South Africa and in Australia. Australia gets the megahertz, South Africa gets the gigahertz. So that's going to be a factor of 10 more sensitive than the VLA right now. I mean, we don't unfortunately know what's happening right now with science funding in the United States, but we are supposed to start, they literally started building the first antenna of the next generation VLA. The VLA, I should mention, is about 40 years old now. It's just, you know, we keep upgrading the instruments, but obviously it's time for the hardware to also just literally have new antennas. That would be actually, they would be built all across North America and have a very huge bandwidth all the way up to millimeter, so millimeter wavelengths. So that's like, you know, 1,000 gigahertz or something like that. So it's going to be a huge bandwidth telescope. It would be very, very cool if it gets off the ground.
I'm always amazed at how much we can see from our little planet.
Yeah, there's a lot of very clever people who've done very nice things that I get to utilize. It's always how standing on the shoulders of giants, right? Is how they put it. Let's see. Is it possible yeah, we already answered that one. Are there any plans to repair the Arecibo Observatory? Unfortunately, no. They were required contractually once Arecibo was just collapsed. Oh, I should have shown I went to Arecibo on my honeymoon. Anyway. The guy actually suggested it anyway, but yeah, so Arecibo, it's unfortunately not really, there wasn't enough money to maintain it to begin with, so that's why it collapsed. And they're actually completely clearing the site now, and they're probably going to have some NGVLA outriggers in Puerto Rico, but they're not going to rebuild Arecibo itself because of the lack of funding, is the unfortunate answer there. So. Let's see, what other questions? I'm kind of scrolling through, so I'm sorry if I missed something. Do solar flares negatively affect the sensitivity of these types of telescopes and such serious damage occurs? The short answer is not, like, we're not going to damage it in terms of like hurt the telescope. There's some frequencies and some data observations that you're not going to take during a solar flare. I didn't get into it, but as you go to the higher radio frequencies, you do start having some atmospheric effects and things like that. So you won't probably take an observation during those times. If you're doing like 1 to 6 gigahertz, though, say single gigahertz on the VLA, it's usually not a problem, is the answer. We're pretty lucky.
Well, thank you so much for your time.
Yeah.
This was super duper interesting, and we were amazed to have so many participants show up. This has been really exciting. Thank you so much.
Thanks for having me. Everybody have a good night, and 7-3.